Hi there, my name is Bella Ben, I'm the lead of JGroups, and today I'm going to be talking about how to run a JGroups cluster on Google Compute Engine. I have two goals. The first goal is to show how to configure JGroups to run successfully on Google Compute Engine, and the second goal is to run a performance test on a cluster of JGroups instances. First, in part one, I'm going to start off with a quick intro to Google Compute Engine. Then I'm going to start two instances, form a mini cluster and run uperf. Uperf is my application that's running the cluster and that benchmarks JGroups. I'm going to be talking about this a little bit more in detail. The second part, I'm going to be running a larger cluster. I'm going to be running 100 instances and hope to get some meaningful performance numbers. In the third part, depending on whether I still have money in my credit card, I'm going to run a large cluster, hopefully 500 plus instances, and also get some performance numbers. Okay, let's go to the Google Developers Console. To do that, you have to sign up, get a Google Compute Engine account, and register, and then basically you sign in, and this is what you see. This would show you the instances that have been started. Here you see all of the disks. I currently have one disk called JGroups disk, and this basically contains JGroups, my configuration files, and other customized stuff like .bash rc, stuff like this. I mount this into my home directory, and if you run a cluster, unfortunately, this disks can only be mounted read-only. So if you want to make a change, you have to stop your cluster and make the change in one read-write mounted disk, unmount it, mount it as read-only again, and then run the cluster. This is not a big problem for our test though. Here you have images. Google provides a couple of default images. I created my own image, which I call JGroups 2. This is based on a default image, but additionally I installed Git, Java, and two or three more small things like iperf and IP track. Okay, here I have a look at my quotas. I already raised them, so I'm allowed to run 1,000 instances. However, I can only run 1,000 CPUs. That means I could run 1,001 CPU instances or 502 CPU instances, and so on and so forth. For the larger test, I hope to be able to run 504 CPU instances. So I actually put in a request to raise this to 2,000, but pending approval, we're going to be running 100 today. Okay, so let's go back and start two instances. We're clicking on new instance. Let's call them box 1 and box 2. I want to run them in the zone called Europe West 1A, and I want to run a standard box. This is the third smallest box that you can get. It has one CPU and 4 gigs of memory. For the performance test later, I'm going to run the configuration called N1 high CPU 4. I'm not interested in that much memory, but I need a lot of CPUs for the test. The more the better, but I'm not going to run 8, I'm just going to run 4. By the way, if you look at the prices of Google Compute Engine, you see that a high CPU 4 with 4 virtual cores costs about 17 cents an hour. So that's actually pretty cheap, I think. So we're now going to choose the image, which is JGroups 2, or choose the disk, which is JGroups disk, but we're going to mount it read-only because we're going to run 2 instances. That's it. Click on create, and box 1 is being created. Now we're creating the second instance called box2, and I'm running it in Europe as well. Same type of machine. I choose the same image and the same disk. Again, the disk has to be mounted as read-only. That's it. Create. We can now look at the status of the two boxes. Will be shown here, and I can SSH into the box, into the boxes. So box 1 and box 2 have been started. Let me see if I can SSH into box 1. This is actually very fast. And SSH into box 2. No, they haven't been started yet. It just shows that the virtual instances are up, but the operating system hasn't started yet. So let me try again. This time it should probably work. Yes. So I'm in box number 1, and here I'm going to go and SSH to box number 2. Okay. As you can see, all the files you can see here have been are basically available on the JGroups disk, mounted read-only. So you can see I have JGroups, and I have a bin directory which contains a reference to the shell that starts my test. So let's take a quick look at the configuration that we're going to be using. This is called Google XML, but because it contains my user ID and password, I'm going to show Google Example XML. So, okay, first of all, you see that the transport is TCP. As all other clouds, Google Compute Engine doesn't allow for IP multicasting. So we have to use TCP, and because we're using TCP, we could use TCP Gossip as the discovery layer using a separate lookup server. We could use TCP ping, which lists all of the servers by IP address statically. It's a little cumbersome though. Or we could use a new protocol I wrote, which is called Google Ping, which takes the access key and the secret access key. This is very similar to EC2. Then it takes a location. This is the name of a bucket that may or may not exist on Google Cloud Storage. I'll show that in a second. And the rest is the same. So what happens is that when a member comes up, it looks up the JGroups bucket, looks for a directory that is named the same as the cluster which we joined, and then reads all of the files in that cluster. And one member writes one file, writes its information, such as, you know, physical IP address, logical address, and all that stuff into one file for others to find it and to read it. The advantage of this is that we only need to have a Google Cloud Storage account, and all of the members actually retrieve that information from that specific bucket and therefore find each other. So let's take a look at, we haven't started any instances yet, but let's take a look at Google Cloud Storage. You can see there's a JGroups bucket. If I click on it, there's this is the image that I'm running of the operating system. This is something else, but there hasn't been any bucket created yet under JGroups bucket. So let's now run uperf, and we're passing in the google.xml properties. We're calling this instance A. Now on the other box, by the way, if we do an F5 here, we see the instance is being started. We see the IP address is 10.240.13.27. That's the internal IP address. And if we click refresh, we see there is a new folder called uperf, which is the name of the cluster. And under it, we have one file containing information about A. This is information about A. And now when B started with the same properties, we're calling it B, it basically reads from this directory, reads this information, sees that A is the first member in the cluster, asks A to join, and we can see that the view changes to AB. You can see the view change here is now AB. This number in brackets here is the number of members in the cluster. So we have 2 members in the cluster. If I do a refresh here, you can see that we have 2 instances now. Okay, now let's run a simple test. So what does uperf do? Uperf basically has every member send n number of messages, currently 20,000. I can change this interactively. I can change it, for example, to 25,000 by pressing 7. And you can see the number of messages that are going to be sent is now 25,000. If I look down here in the other instance, I can also see that the number was dynamically changed to 25,000. So what does the application do? It invokes 25,000 RPCs, synchronous RPCs, and with an 80% chance, it does a read, and with a 20% chance, it does a write. A read is basically an invocation of a method called get that returns 1,000 bytes. So the message size by default is 1K, 1,000 bytes. A write is by default contacting 2 members and invoking a method called put and carrying with it in the RPC, it carries 1,000 bytes as well. So everybody invokes 25,000. Let's now do this. I press 1, enter. Everybody invokes 25,000 RPCs, and when done, where I invoked it, the first member is basically grabbing the results from all of the members and averaging the results. So here we can see A itself invoked 2,718 requests per second for a total of about 19,000 reads and 5,000 puts. B invoked about the same number of requests per second, 2,700 for a total of 19,000 gets and 5,100 puts. So the average here is 2,721 requests per second per node. That means we were able to invoke 1 request every 0.37 milliseconds. If we run this again, of course, this is going to be faster. You can see the results are now 6,500. Also, of course, this depends on the machine type. Now 8,600 and so forth. So let's kill this. And by the way, when I kill this and I do a refresh here on Google Cloud Storage, you see that now I only have 1 file left in here. And the view down here changed to B. All right, let's actually kill those 2 boxes and run. Actually, we're gonna leave, and run a larger test. So, okay, one more thing I wanted to show is that you can actually get information about the instances that are running. I'm gonna run uperf again. And I'm going to run uperf here. And when I SSH into a box, let's say box 1, I can run a so-called probe. Probe fetches information about the running members. So when I just pass in the address of one of the 2, because LP multicasting is not available, unfortunately, we have to pass in the address of one of the 2 members. We get information about the 2 members. Member 1, this is local address is B, and member 2, local address is A. Now we can do much more powerful stuff. We can, for example, say, get me all of the attributes of protocol unicast 3. And here you see all of the attributes. Now I'm mainly interested in num messages. So we can see we have number of messages sent, number of messages received. showing this for both members, A and B, and if we run the performance test, you will see that those numbers change. You can now see that this figure has changed. Okay, this is it for the first part. In the second part, I'm going to be talking about, I'm going to be demonstrating how to run 100 instances. Stay tuned.